Hi, everybody. Welcome. Thank you very much for joining us today for another IBIPSA education webinar. Today, I'm delighted to have with us Xiaoxiong Xie, who is here from the University of Plymouth. Xiaoxiong won the CIBSE Building Simulation Award for his work on this topic. So it's great to see an example of some really first-class simulation work. And today we're going to be talking about multi-scale modelling of buildings in urban environments. And what's really interesting about this work is the focus on the external environment as well as the internal environment. I won't say any more about it. I will leave Xiaoxiao to introduce himself and his work in a little bit more detail. And instead, I will introduce the IBIPSA Education Committee. So if you haven't been to one of these before, you might be wondering what the Education Committee does. But we exist to identify education and training needs throughout the building simulation community, and that's a very broad community. We initiate and we develop and encourage new education materials and methods. And the training sessions that we offer are open to non-members as well as to members. So anyone can register for these sessions and anyone can access the recordings afterwards on our YouTube channel. And we also aim to promote the development and sharing of best practices in BPS education. And we'll be talking more about that at Building Simulation 2025 in Brisbane next month. So if you're able to join us for that, that would be fantastic. If you have any ideas for webinars or training needs, anything that you would like to share, then do please drop me an email. You'll have my contact details from your registration confirmation email. So the format for this webinar is the one that we usually use. We're going to start in a minute with Xiaoxiong's presentation, and when that's finished, we'll have some time for questions and answers. As usual, if you could pop your questions and answers in the Q&A box, and I will put the questions to Xiaoxiong once he's finished his presentation. So just if something occurs to you while we're in the course of the presentation, do just pop it into the box and I will ask the question on your behalf. So without any further ado, I will stop sharing my screen and invite Xiaoxiao to share his screen and start the presentation.
Yeah, thanks, Pamela. So I'll share my screen.
That's great.
Yeah, okay. And so firstly, thanks, Pamela, for inviting me to this talk. I'm really happy to have this chance to share my work. So my background is architectural engineering, but I went through my PhD in writing. I did something about the urban climate as well. So mostly what I focus on is on the interaction between buildings and the urban climate. So basically it's the interaction between indoors and outdoors. And also I was in a couple of conferences earlier this month, the one in the building simulation, one in the urban climate. And what I feel is that these two groups or two communities, they are pretty interested about each other's work. Like for the building researchers, they are interested about how the climate could impact the buildings. And for the urban climate researchers, they are also interested about how could the buildings influence the outdoor climate. So I think therefore I think it's pretty interesting topic. So hopefully it's helpful for your own work. And the topic of my talk is the multi-scale modeling of buildings in urban environments. So that's basically what I will mostly focus on. So I just start with some news we've been reading recently. So because in recent years, when we read news, I personally, I got feeling that we are seeing more and more news like this. For example, which year, the current year was the warmest year ever, or it's the hottest summer we've been experienced, or it's the hottest one on record. And but this one is for 2022, and it was the thing as the warmest year ever. So in 2023's January. So basically, is that in January, the Met Office or other departments of the weathers, they post this kind of news because they have the full record of the last year, so they can confirm that the last year is already becomes the warmest on record. But again, on the next year, 2023, it was confirmed as the world's hottest year on record. And then in 2024, it was further confirmed that the summer was the world's hottest on record. And then 2025, this year in January, it has been found that January was already become the warmest January on record. So latest news is that the UK's Met Office, they have concluded that extreme weathers is becoming the UK's new normal. So in the past, we feel that the UK typically has mild climate and we don't really need air conditioners in summer because the temperature is pretty temperate. But now we are experiencing several high heat waves, especially during the last several weeks. So we are feeling that probably in the future, we are sh- generally gradually shifting from the heating dominant climate to both heating and cooling climate. Because as I remember, one study have found that by climate projection in the future, the London's climate will be something like the current day's Madrid. So we we may have seen this temperature strip before, so that's designed by Professor Ed Hawkins from the University of Reading. So this is the pretty straightforward representation of the climate change. So how the global air temperature has been increasing from the past to until the recent days. So you can see the past it's showing in dark blue colors, which means January is very cool, and now as it's approaching the recent years, is the darker of this becoming a darker white. And when we look at the exact value of global temperature change, we can see that since around the 1970s, the global air temperature has been increasing rapidly until the recent years we have reached several peak level of air temperatures. And the heat will cause the death because as the temperature increase, firstly, people will feel discomfort and then get some head stress and even head stroke. Eventually, that will lead to death, especially for the vulnerable groups like the elderly persons. So this the survey in France. It's calculating the number of deaths for different age groups and the location of mortality relevant to the heat. So we can see that the deaths happen at home. Actually, it contributes a large proportion, and also it's around half of the total extra deaths due to the heat. So that makes us more cautious about the heat resilience of the buildings because, for example, in the UK or in the other European countries, traditionally we are focused on the heating, but nowadays the overheating is becoming a new issue. So there are lots of studies recently focused on the overheating of buildings and the guidance like the CIBSE environmental guide A, they start to have more detailed standards or criteria to assess the indoor overheating risk. And the building simulation is the important way to assess or predict the building overheating risk and also to assess the impact of different passive cooling interventions or even energy saving potential for cooling. But the building energy simulations, the important input variable is the outdoor weather condition. And typically, how we get the weather data is from the rural weather stations. For example, we use the typical meteorological year data. They are all using the last maybe 30 years data from the standard WMO weather stations, but the location of WMO weather station has the strict criteria. Typically, for example, for London, we have lots of standard weather stations. For example, the most famous one probably is the Heathrow Airport, which is used for weather forecast as well. And also for the city center one, we have the St. James Park. But still, we feel that both of the Heathrow Airport and St. James Park, they are actually have very similar surface types. They're all very short grass. So that's basically the requirement of the WMO weather stations because it's required to locate it over short, well-watered green grass, and it should be free from the influence of the non-meteorological factors on the readings because it's try to exclude like the factors like the buildings or anthropogenic heat. And finally, the purpose of these WMO weather stations are to monitor the weather and climates in the regional scale. So just like when we look at the weather forecast, it says that London is forecasted to have the temperature of some degree to a certain degree. So that's for typically for a regional weather forecast. But for building simulation, I think in most conditions, we are looking at the urban buildings because the city is the form of buildings. So most of buildings, which means most of the buildings occurs in the urban area. But if we are using the weather data from these kind of relatively rural stations like Heathrow Airport, the question is the whether it's representative enough for a building in the center of the city of London. And when we talk about the urban climate, the one of the most well-studied phenomenon is the urban heat island. But when you talk actually when I talk to the meteorologist about urban heat island, they usually ask me what kind of urban heat island are you talking about? If it's the boundary layer urban heat island, or it's the surface urban heat island, or it's the subsurface urban heat island, or it's the canopy layer urban heat island. So when we use the term urban heat island, usually we just refer to the canopy layer urban heat island, so that the layers is relevant to another pretty important concept for the urban climate. So when we studying urban climates, one of the most important thing is about the scale. So which scale are we looking at? So for the regional, we have the largest one, we have the meso scale, so or regional scale. So this usually for the weather forecast, and it's usually covering a whole city and its surrounding areas. And when we zoomed in, we have the local scale. So local scale or neighborhood scale is comprises of buildings and streets. And when we zoom in again, we get micro scale. So it's consists of the building and its surrounding microclimate. So micro scale is typically what we as the building researchers are most interested about because it's just the exact surroundings of the building itself. So we're trying to understand. That's also an important factor of the input for the building energy simulation. And so there are some drivers for the urban heat island. So I just distinguish that into the urban form and the urban function. So for a city, if there's no people living in the city or it's an empty city, it will still have the urban heat island. So that's about urban form. For the urban area, we have the unique surface characteristics, which is distinguished from its surrounding rural area. The one is the building fraction and it's called impervious surfaces, which have the very limited evaporation cooling effect. And also the urban geometry, like the straight cayenne that will shape the wind and also radiation components. And we have the building fabric or urban fabric, which made of concrete or brick blocks, different materials that have the very high possibility emissivity and high heat capacity compared to the vegetations. So these factors are the urban form factors contributing to the urban heat island. And for the urban function, it's more about the human activities. So this typically include the buildings, the industry, and the transport. So all of this will consume for example, fossil fuels and generate both of the waste heat and other kind of heat to the environment. So that's about the urban function. So all of these factors together, they shape the canopy layer urban heat island. And for the building in an urban environment is influenced by different factors. So for example, when we look at this red circle is the assumed of building of interest we are going to study. It's influenced by the surrounding environments. Firstly, the surrounding buildings will have the overshadowing effect on it, so it blocks the solar radiation. And also the surrounding surfaces, due to the surface temperature differences, there will be the long-wave radiation exchange between the target building and the other surfaces. And also the surrounding buildings will have the wind shattering effect, which influence the convection heat transfer of the building surfaces and also the ventilation heat transfer. Some vegetation areas, they may provide some little cool island within the cities, and the building fabric have the heat storage, and also there are some heat emissions from the human activities. So all of these factors need to be considered when we simulating a building in an urban area. When we talk about the interaction between buildings and its surrounding urban areas, typically this relationship is mutual, it's two-way. So the urban climate will influence buildings in terms of the energy performance, and also the indoor thermal comfort, sometimes the indoor air quality, and then the buildings in turn will influence the outdoor climate due to the heat emissions or air pollutions. However, a gap in the existing methods is to overlooking the impact of urban factors on the building thermal or energy performance. So this figure shows how the different urban scale factors impact the building scale factors and finally influence the indoor thermal environment. There are several challenges in the current studies. The first one is about the long-wave radiation trapping. So what is the impact of interbuilding long-wave radiation exchange be for the building performance? And the second is about the urban wind and air temperature, and also importantly about the vertical profiles, because it's not just about the wind speed or air temperature at a certain height, it's about the whole profile. How will this influence the performance of buildings or influence the input for the building simulations? And the third one is the feedback of building anthropogenic heat emissions to outdoors. Because traditionally, when we run building simulations, we only use the weather data as the input. So it's a one-way process. We input the weather data and we get the results, and there will be no influence back to the weather data. But actually, in the reality, the building itself also generate heat, which will influence the outdoor climate as well. So I think these are three challenges in terms of the building simulations. So we just talk about this one by one. So first about the long wave radiation. And a typical assumption in lots of building energy simulation too is that the adjacent building surface temperature is equal to the air temperature because it's very difficult to obtain the actual surface temperature of the surrounding buildings. But the observations suggest that the building surface temperature can be much higher compared to the air temperature, especially for the south-facing facades, which can be around 15 to 20 degree warmer compared to the air temperature, so which is well known. So this means using the air temperature to represent the surrounding building surfaces will lead to some certain biases. There are some existing methods trying to model the interbuilding long-wave radiation. And the first one is the couple with urban climate models. For example, there are some studies coupling building energy simulation tools like Energy Plus with some urban climate models like AmiMat. But this is typically complex because models like MMite it's a CFD-based model, so it's very computationally expensive. Typically, running a model like this will take lots of time. For example, running a 7 days case will probably take more than 3 days. Another way is for the building agent simulation tools only. So these tools like Plus, they made some assumptions to compromise. So firstly is assuming the adjacent building surface temperature is equals to the air temperature. So that's the default option in Plus, and is the most widely used in most of the studies. Or secondly, assume that adjacent buildings are isolated, so they have the surface temperatures as an isolated building. But both methods can cause large biases due to the difference between the air temperature and surface temperatures. But still, the main difficulty is to obtain the surface temperature of adjacent buildings. And here, we proposed an approach, which is the using an iterative approach to assume that we have the building in the idealized neighborhood, which is made of the identical buildings. So in this case, we assume that all of the buildings should have have the same surface temperatures. For example, the surface temperatures of this source wall of the target building should be the same as the source wall surface temperature of this adjacent building because all of the buildings are assumed as the same. But it's still a compromise, but it's a kind of one step ahead from the default assumption. So using this approach, so basically, first they will assume that we assign the initial surface temperature to the surrounding buildings. For example, whether it's the air temperature or it's the isolated surface temperature. And we run the simulation. And in this case, we need the view factors and the surface temperature as a schedule to be inputted to Plus. So there's a function called environmental parameters in Plus, which could be used to calculate the long wave radiation. So by doing so, we can have the updated surface temperature of the target building, which already consider about the effect of long wave radiation from the surrounding environment. And after this run, we assign the surface temperature of the target buildings again back to the surrounding buildings just to update the surrounding buildings, and we run the model again. And eventually, we should get model convergence, and we get the results that all of the buildings in the neighborhood they have they have the same surface temperatures. So that's for the kind of the idealized scenario. And we have validated our results with the observations. So we used um, this is the concrete block size located in Japan, and they have the observations of the surface temperatures of these blocks. So this basically showing you a similar setup as our assumptions, which is the idealized neighborhood with identical buildings. When we compare our modeled surface temperatures of each facet with the observations, we found that by using the default settings of Plus, which is showing the blue color, so this is using assumption that surrounding buildings have the surface temperatures equal to the air temperature. So we found that it will largely underpredict the surface temperatures of these concrete blocks. And by using the updated approach, the iterative one that we've proposed, we see some increases in the surface temperature, which makes the results closer to the observations. But still, we see some gaps here, which can be due to the differences in the ground surface temperatures or the thermal characteristics of the concrete and so on. But still, we see some improvements from default method to the observations. And we are interested about how the long wave radiation exchanges between the target building and surrounding environment will impact on the building itself, because it's largely overlooked in the past studies. So we consider three plane area fractions for building densities from 0.1 to 0.6, which is representing a typical open space to a typical dense neighborhood. And we consider three locations, which is the Aberdeen, London, and Marseille. So these basically these three cities have the similar climates, but they have the different latitudes. So this to compare the impact of latitudes or solar altitude on the long radiation impacts. The results we found that so firstly we look at the left one, which is about the north-facing wall surface temperatures at different building densities in London, and this is showing the temperature difference between between updated method and the default method. So we can see that in summer, we see a temperature difference of around up to 4 degrees in during the noon time. So this is the improved method surface temperatures. And in winter, we see some differences, but still, although the value is smaller, it still have the value of around 1 degree compared to the default scenario. So this is basically indicating that as the neighborhood becomes denser, the impact of long wave radiation is larger because of the view angle. So because the long radiation is a function of the surface temperature and the view factor between the target building and the surrounding surfaces. As the buildings getting closer, we have the larger values of the view factor or view angle. That will increase the impact of the long radiation. And when we look at different climates from Aberdeen to Marseille, so it's from the high latitude to a low latitude, so or it's about the uh, um, small solar angle to a large solar angle. We can also see that in Aberdeen, the difference between the updated method and the default method, they have the relatively smaller difference in the surface air temperature. And in Marseille, this impact is larger. That's because of the impact of the solar radiation. So when we have the high solar position, there will be more solar radiation on the south surface of the building, and that will lead to a larger surface temperature difference between the south surface of the surrounding buildings and the target building's north surface. So that's basically lead to larger differences in terms of the long wave radiation. So this is the basically how the long wave radiation will impact on surface temperature. And when we step ahead to look at how will this impact on the indoors. So here we use the internal cooling and heating load as an example. For example, we look at London and set the heating and cooling set point of 20 degree and 27 degree, and we found that there's actually make some differences. The load difference between the updated method and the default method shows the difference of 4 volts per square meters for the summer cooling load. And in winter, it have the up to around 1.5 volts per square meters in terms of the heating load. So when we look at the percentage difference of the energy demand, so this equals to the annual cooling energy consumption of around 13% higher and the annual heating energy consumption of 5% lower. And when we think about the threshold set by ASHRAE standard 14, which is the criteria for building energy simulation, it's typically an area above 10%. It should be seen as a large one. So typically for this cooling energy consumption, the 13% difference is something that we should be careful about. So basically, it's indicating that the long radiation, although it has been largely overlooked in the previous studies, it still should have some certain impacts on the building performance, especially for the dense neighborhoods or for the low latitude cities, because they're receiving more solar radiation on the surrounding building surfaces. So therefore, it's a factor that we need to consider about. But still, the challenge is that this study we only look at the kind of the homogeneous neighborhood, but in reality, most of the buildings are heterogeneous because of the buildings are different. And the surface, the color of the surface, the materials, they could also be different, which means the surface temperatures should have the large variation. So this is the future work that we are going to look at. And the second challenge is the urban air temperature and wind speed, as well as their vertical profiles. How will this impact on the building energy performance? There are also different ways to assess this kind of urban life impact. Okay. Yeah, so I'll just start from this slide. Sorry about the internet. And so here the model we are using is called SUIS. So in full, it's the Surface Urban Energy and Water Balance Scheme. So it's based on the urban energy balance. So where we have for the urban surface, we have the incoming energy of the night UV radiation and also the anthropogenic heat, which is generated from the human activities. And for the output, we have the sensible heat flux, which is a QH, and latent heat flux as QE, and we have net storage heat flux in the urban surface, which is the delta QS. So how SUIS is modeling? So basically, it requires the inputs pretty similar to the building simulations like Ng Plus. It also requires two sets of inputs data. The first is the climate forcing data, and second is the surface characteristics. And with this information, the SUIS can model the surface energy fluxes and therefore derive the wind temperature and humidity profiles within the urban canopy layer. The SUIS considers 7 surface types and is the 1D model, which only considers the vertical variability, but not the horizontal. So in horizontal, it seems that it's modeling horizontal average values, but we only have the vertical differences. But because it's the 1D model, which makes it very computational efficient, and when combined with Ng Plus, it's basically very fast. Typically for SUIS run, if we're going to run a SUIS for a whole year, it typically only takes around 1 minute. So that's very fast. The SUIS model itself has been evaluated in different climates globally. So for the wind speed profile here, so it's evaluated in several European countries, including the Gothenburg and the Basel. So it's basically showing pretty good agreements because here the right line is the wind profile modeled by SUIS, and the black dots are the observations. And for the air temperature profile, we have 2 air temperature sensors in London, close to a KCL site. So we have the air temperature observations compared to the simulations. There's around 1 degrees the mean absolute area. So generally, the model is providing the air temperatures lower consistently compared to the observations, which is also acceptable as the physical model. And another thing we need to look at the wind profile is its shape, because typically when we do building simulations in Ng Plus, it provides a parallel profile which has an exponent and the factor called the boundary layer depth. But in reality, the wind profile is quite complex. So when we look at the right figure, the dots here shows the measured points. And we can see that beyond the urban canopy layer, which has the height of the main building height, the profile is following a log law, but within the urban canopy layer, which is height below the building height, it follows the exponential law. So it's quite different from the anti-blast because typically the building simulations they adopt a simpler format, which is easier for the use. And the workflow of SUIS anti-blast coupling is that the SUIS they use these inputs and models the air temperature, relative humidity, and wind speed. These values provided are actually for different heights within the urban canopy layer, but the Ant Plus only requires the weather data for the air temperature at 2 meters, relative humidity at 2 meters, and wind speed at 10 meters. So we also need to provide another set of coefficients, which is the air temperature and wind speed vertical profile coefficients, which is following the power law of Ng plus, so that that can be used directly without need to it doesn't need any changes to the source code of Ng plus. So with this information, Ng plus can models the indoor thermal environment and the indoor earthing risks. Now let's get back to this relationship between the urban scale factors and building scale factors. So we just talk about the long radiation trapping using the iterative approach, and now we have additionally have the wind sheltering effect and warm air temperature considered with the Swiss modeling. And the one problem, the one question we're interested is about how does this each individual urban factors can influence the building energy performance. So we look at three climates, including Singapore, which represents a low latitude city, Shanghai, which represents the mid latitude city, and London as the high latitude city. And we use the TMY data for the climate forcing data for Swiss, because typically Swiss requires the the forcing data from the certain height above the roughness sublayer so that it's not influenced by the urban surface. So the rural sites, they are pretty ideal for this case. And here we assume the building plan area density of 0.6 representing a quite dense neighborhood. And for the cases, we are trying to think about what are the most common cases existing in the current research. So first is the rural. So rural is basically we are just use the rural weather data and we assume the building is isolated. And then we have the urbanized air temperature and plus the shading, which is shown in ice. We have long radiation additionally considered. And we have the wind speed considered. And finally, all of these four factors considered. For metrics, we use the indoor heating risk and also the cooling and heating demand. When we look at the wind profiles modeled by Swiss, so we can see the blue line here is typically showing the exponential law, but the N plus by default is the power law. So what we can do is we just fit the curve using the power law and we just get the coefficients, which can be used in H plus directly. Similarly for the air temperature, so N plus assume the very small value of temperature gradient, but the Swiss provides the larger one due to the larger temperature variations within the urban canopy layer. As the results, we look at the indoor heating risk firstly. So we can see for different climates, the rural setting is largely under predicting the heating risk, but this can vary between different climates. And also, we found that there's the each individual factor, urban factor, is pretty important. For example, if we just missed the urban wind speed, we can have the around 15% of under prediction for Singapore case, and for London case, the value is much higher because London has a relatively high wind speed. Again, when we look at the cooling and heating demand, it's showing quite similar patterns. So basically, uh, it's indicating that each individual urban factors is important in the building energy simulations. So we need to consider all of these. So therefore, we need a holistic or comprehensive approach when we're doing the building simulations. And now we come to the third challenge, which is the building anthropogenic heat feedback. Just a bit background, so the building energy is a large contribution to the global heat emission, CO2 emissions, and a key goal to achieve net zero is replacing the heat pumps, replacing the air gas boilers with heat pumps. Well, the heat pumps, when they providing cooling, they just remove heat, from indoors to outdoors, and when predicting heating, it's opposite. So there's a risk that in the future, when the UK has both heat and cooling climate, uh, that could increase the outdoor temperature due to the using of the air source heat pump, or decrease the winter air temperature due to the heating with air source heat pump. So here we consider an updated definition of building atmospheric heat emissions, which is basically calculating the waste heat from the buildings by by calculating the difference between the unoccupied building and an unoccupied building. So basically, that's the amount of the heat released from buildings, and this value we can easily obtain from the N+ simulation. And as the feedback, we have the workflow from Swiss to Ng Plus, and now the Ng Plus provides the building heat emission, and we can put that value back to Swiss to the climate forcing data, so that the Swiss can model the update the air temperature, considering this kind of building heat emission effect. And as the scenario, we look at the two common building types in the UK, which are the flats and the detached house. And we use the realistic building occupancy behavior, considering an elderly couple at home throughout the day, and they only use the air source heat pump or gas boilers when the rooms are unoccupied. So it's typically a optimistic scenario. And we look at 9 UK locations from the south, which is Plymouth, to North Aberdeen. And because we are looking at the future scenario of 2050s, we use the climate projection from the UK CP09. And here are the results of the building heat emissions by using gas boilers or air source heat pumps. So we can see that during winter time, the red line here, which is representing the gas boilers, have the pretty high value compared to the air source heat pumps. But the air source heat pumps, they have the higher value typically in summer due to the cooling. And when we look at the outcomes of replacing boilers with air source heat pumps on the outdoor local climate, we can see the outdoor air temperature can be increased by around 0.12 degree in summer and decreased by 0.15 degree in winter. So that's because the air source heat pump is releasing heat to outdoors or absorbing heat from the outdoors. These values are quite small actually, but we are still looking at the residential neighborhood with low-rise buildings. And in center London, for example, with the high-rise commercial buildings, we expect this impact could be larger. And also in different climates, we found that this pattern is largely follows the demand of cooling or heating. So it's basically increase as the summertime temperature increase is decreasing as it's going north, and in the winter it's opposite. So as the summary for this study, so basically it's the one step forward from the one-way coupling that we further consider the feedback from buildings to urban environment. And by replacing the boilers with air source heat pumps, we can see there's some increase in outdoor air temperature and decrease in outdoor air temperature in winter. These values can have some certain unintended risk, increases in risk of summer overheating or winter overcooling. And this should be particularly important for vulnerable households, because there might be a case that the certain households could not afford an air source heat pump, but when its neighbors are using this will impact their own thermal performance or their own thermal comfort and energy bills. So that's another study that we are working on. So some final tips for how to use Swiss. If you are interested, the Swiss is the open source software, or is the Python package exactly. So there's a very complete user's guide, so you can just Google it, and on GitHub you can see the full source code of Swiss. And basically, because there is the Python package, it basically need only a few lines to run the model, but um, it requires some certain input coefficients, which is not, some of them can be easily obtained, but some are not. So what we are currently working on is to create the database that including the different set of example input factors that for the users to use. And for the feedback, so the Ansible just provides the building heat emissions, which can be added to the climate forcing data of Swiss, and Swiss run the model to generate the EPW file again for Ansible simulation. So that's it for my talk. Thank you for listening, and I'm happy for any questions.
Thank you, Xiaoxiong. That was a huge amount of information, an awful lot of work there, summarized very succinctly. Thank you very much. We have a question in the chat, but before we come to that, I'm going to use the chair's privilege and ask one of my own first. So in this, you've been looking at sort of three different factors which are all having an impact on potentially on energy demand, certainly the first two. But obviously we're increasing the complexity of the modelling by taking account of each of these factors. And if you had to pick one of these, do you think, which one would you say is the priority for addressing in our modelling? Which ones would be nice to have?
Yeah. So the factors here, we just talked about including the urbanized air temperature, wind speed, and also additionally the long wave radiation. And long wave radiation, based on the results we have, we see a difference in terms of the heating energy about 13% and the cooling energy about 4% only. So this, if we look at the cooling energy only, this is typically a smaller value compared to the other factors. Uh, so for me, I think the important factors here is the air temperature and the wind speed in the urban area, because the air temperature, they could be the urban heat island intensity could be sometimes around 2 degrees in certain cities like London. And so that will make a large difference to the building energy performance. And also the wind speed, it could be largely decreased due to the urban impacts. So that will largely impact the different factors like the ventilation rate as well. So that's one I think most important here.
Thank you.
Also, yeah, sorry, it's because this will only request to modify the weather data. So I think that should be relatively more straightforward. Yeah,
Yep,
yeah.
great. I'm going to go to questions from the audience now. Just a reminder, we probably have time for maybe one more in addition to the two we already have. So if you have a burning question, do please pop it into the Q&A. So the first question is about using different modelling packages. So in particular, if you're using Passive House planning package and design pH for modelling overheatings, is there any way that you can take this approach that you've been developing, which is obviously based around coupling Energy Plus with Suez and so on, and do something similar to address potential limitations of those packages as well?
Yeah, so I'm not quite familiar with this packages, but that's basically what we are thinking about is what the input are required for this kind of packages. For example, I think lots of packages they require the weather data of the local climate. So I think um, just like I mentioned about the importance of air temperature and the wind speed for the urban area, I think it's a very useful starting point that we use the updated weather data file, especially for the location of interest, not using a weather data from the airport, which is quite far away from where we're looking at. Yeah.
Thank you. I think that's very good advice as a starting point. So I hope that's useful for Tom there. So the second question that we have from the audience is from Milad, who is asking, for this method, do you consider the heat release from other parts of the building, like refraction or reflection of solar from the facade. So both long and short wave radiation and those effects on outdoor air temperature.
Well, uh, so firstly, for the building simulations, we consider the long radiation from the surrounding surfaces, and also in terms of the short wave radiation, because in edge clouds we can just simulate the surrounding buildings as the shading objects, which will have the block effect of the solar radiation. And also we have the option to set the reflectance for the surrounding building surfaces. So in this way, we can consider this kind of the solar reflected solar radiation as well. And regarding the impact on the outdoor air temperature, so in Swiss model, when we look at the energy balance, the incoming energy, it has the factor of the net outward radiation, which includes this basically calculated with the incoming short and long wave radiation as well as outgoing short and long wave radiations. So, but this is it's for because Swiss is the local scale or neighborhood scale model, so it's focused on a certain area which is around have the spatial resolution of around 100 meters to 1 kilometers. So it's about more about the urban surface than the building itself. So if we look at this scale, this kind of long wave radiation and short wave radiation impacts are all considered in the urban energy balance, and therefore they are considered in the outdoor air temperature. But when we look at the local scale, so that's another important consideration of the scales. So when we look at the building scale, the incoming long radiation, which is not essentially same as what the urban surface is received because of the more detailed geometries or urban morphology surrounding buildings. So we can now see that the amount of radiation received by the building is the same as the energy received by the urban area. So I think that's the two scales differences. But if I talk about the model itself, the outdoor air temperature, it already considers the impact of both short and long wave radiations. Yeah.
Thank you. And another great question, which I think might be the same as one that I was wanting to ask myself, which is um, if you're moving from sort of single building modeling to modeling groups of buildings, how do you do that? And how would that be integrated with the modelling framework that you have been setting out here? So, sort of moving towards urban building energy modelling and updating that.
Yeah. Um, so the so if it's talking about the modeling of group of buildings, I assume it's about the urban building energy modeling. So in that case, because the concept of urban building energy modeling is quite similar as energy plus or single building energy modeling, but it's just look at the several different buildings at the same time with some simplified assumption for each individual buildings, but it still needs input of the weather data. So as long as we have consistent coefficients between these buildings with the settings in the urban climate model like Swiss, we can still provide the weather data of this neighborhood for the urban building edge simulations. Yeah.
Thank you. And for the long wave radiation, how would you propose approaching that?
Yeah, long variation is more challenging because just like I've mentioned in my presentation, so we just assume a homogeneous neighborhood which have identical buildings, so that's more straightforward for us to calculate. But for different if it's for neighborhood, especially if it's a real case, we will have the very different building surfaces or materials or colors, which are impacting the surface temperatures. So I think it's still currently a pretty challenging part for the urban building energy simulation. I know there are some work going on to provide the neighborhood scale very detailed surface temperature models, but still they are all, as I know, they are all still in progress, and hopefully we can see how we can integrate them in the future. Yeah.
Yeah, thank you so much. There's another couple of questions which I'm afraid I think we are not going to have time for just now, but Xiaoxiong, if you're happy, we can answer those in the description on YouTube
Yeah.
so that we make sure that people don't miss out. There's just about a minute and a half left now, in fact, less than that, for me to just finish up by saying where you'll be able to find the recording for this webinar. So that will be on our YouTube channel, which is at CIBSE University. And you'll get a link to that in the email that comes to you after this session. And that video should be live tomorrow. And do subscribe to the channel to be kept up to date with when new content is added. We are adding stuff all the time, and you can go back and see the whole history of all of the webinars that we have hosted over the past 5 or 6 years now. And then finally, it remains for me to say, please do consider joining CIBSE as a supporting member. So our supporting members receive a print subscription to the Journal of Building Performance Simulation or online access to the journal only, depending on which version they choose. They also get the right to use the CIBSE supporting member logo. I say this every time, but the prices still haven't changed. These are still our pre-COVID prices, so it's remarkably good value, and you can find out more at www.ibpse.org/membership. So there's no more time left, so I think all I can do is to thank Xiaoxiong again for a fascinating presentation and thank the audience for some great questions. Thank you, everybody. Until
Thank you so
next
much.
time.
Thank
Thank
you.
you. Bye.
Bye.